Hi, everyone. Thank you so much for being here for the first day of the AI Day. Now we're having João Gante from Hugging Face. Give him a round of applause.
Hello, everyone. I'm here to talk about large language models. My name is João Gante, and I'm from Hugging Face, which is a company I hope you are familiar about. If you are not familiar about yet, you'll be in the future. My talk is about bigger is not always better. You'll see why the name of the talk in one or two slides. And then I'll talk about recent advances in text generation, so large language models. So what does it take to train a large language model, which is LLM for short? So you need three pieces. You need the model itself, which is built from the well-known transformers architecture. You need data, a lot of data, and you need compute, specialized hardware. CPUs will not work here in the sense that they are not efficient enough, and you'll get poor really fast if you try to train them on CPUs. So you'll need GPUs or even more specialized hardware like TPUs from Google. So if you go to early 2020, you'll see scaling laws like the ones, oh, I'm sorry, I'm in front of the screen. You'll see scaling laws like this one. You have on the y-axis the loss, which is a measure of how good the model is. Lower is better. And on the x-axis, it shows how the loss evolves as you scale compute, data, and model size. And as you can clearly see on these images, more compute equals better model, more data equals better model, larger model equals better model. So you just increase the size of things, you have a better model, problem solved, right? Bigger equals better. End of the talk. Goodbye, everyone. Just kidding. This was 2020. In 2024, or all the way up to 2024, we have realized that bigger is not always better. The scaling laws are not as linear. What we saw in the previous images is true, but it's hard to achieve in practice. So it's hard to go from theory to practice. Why? On the modeling side, we know that bigger is better, but large models are not only extremely expensive to train, but they are also very expensive to run. So it's not just a matter of training the model, it's also a matter of using the model after it is trained. With respect to data, it's hard to find more data. We have extinguished the low-hanging fruit of text data, and what can we do to get more text data to train our models? We are also been finding that quality is better than quantity. To give you some idea, most of these models up until last year, they saw each data point once during train time. And we have realized recently that if we filter the data for quality and then make the model see each data point a couple of times, the resulting model is better. So the model sees a smaller variability of data, but the resulting model is better because you filter garbage data. If you go on Reddit or 4chan, you probably see a lot of low-quality text, and filtering out that low-quality text, you'll get a much better model. You also have problems with respect to compute. It's easy to scale the quality of the models with compute, but it is extremely expensive. When this whole LLM revolution started, a university, you could do model training as a research project in your own personal computer. Nowadays, you need servers to do it. Or maybe not, we shall see. So if we go from GPT-1 to GPT-4, so these popular models from OpenAI, we see that GPT-1 had a relatively small data set with 1 to 2 billion tokens. By the way, a token is, if you don't know what a token is exactly, you can think about it as a word. It's not exactly a word, it's a subcomponent of a word, but you can roughly approximate it as a word. So GPT-1 saw 1 to 2 billion tokens, and it had a model size that did not reach 1 billion. And as you go down from GPT-1 all the way to GPT-4, you can see that things escalate really, really quickly. It is estimated that the cost to train GPT-4 was around $100 million. And this training cost is the successful run. It does not take into account all the runs that failed, all the experiments, all the engineering costs, all the costs to set up the infrastructure. It's just the successful training run. It's extremely expensive. To give you some ballpark, it is as expensive to train GPT-4 as to buy a very large commercial airplane. It's in the same ballpark as a GPS satellite. It is extremely expensive to train these models, and we are not taking into account running these models, just training the model, having the model ready to you. Inference also got much more expensive. It didn't grow at the same pace as training did, but it also grew very quickly. And of course, inference scales proportionally to the amount of use you give to the model, and as these models become more popular, the cost increases as well, because every time you request a token, you have to pay something. We can see that the cost of running GPT-1 to GPT-4, just getting one token got at least 10,000 times more expensive, with the caveat that as the model size grew, the time to generate one token also grew. So not only you need more devices to run your model, each token is also slower to obtain. So, yep, we are poor. It's extremely difficult to handle large language models. Or maybe not. In reality, I wanted to show you this table. It's a performance table from a model that is highlighted, came out this week. The rightmost column is a benchmark that is used to evaluate large language models. There are many different benchmarks. This is just one of them. And we can see that this model in orange is as good as these very popular proprietary models, with the difference that you can run this model in orange in your own computer. It has to be a large computer, yes, but you can do it. So you don't need a giant server to run GPT-4. You can have GPT-4-like quality on your desktop, as long as it is a big desktop, of course. So how did we democratize access? By we, I don't mean Hugging Face. I mean we, the community, the ML engineers around the world. There are 4 things I want to talk about. I want to talk about quantization, which is the act of making the same model smaller from a compute perspective. I want to talk about optimization, which is the act of making a thing that we have run faster. I want to talk about architecture, so how have we changed the model such that it has a higher quality? And I want to talk about training. What did we change about training to democratize access to machine learning models? But before, I'm not sure how familiar you are with the large language models, so I want to give you a primer to highlight a few things that you should know about so you can understand the rest of this talk. Don't worry, I'll try to be not too technical. It's impossible to be not technical at all, but I'll try to keep it light. So if you study machine learning models, you'll probably see this image. You don't need to know everything that's in the image. I just want to highlight a few things. So ignore the block on the left. You just need to take care of the rightmost block. This is what an LLM nowadays is. This image, by the way, is from a very popular paper, one of the papers that made these transform architectures really popular. So you ignore the pieces on the left. On the pieces of the right, I want you to know that the input to the model is the text that you send to the model, plus the text that the model has been generating. Because the process of generating text is regressive, or more precisely, autoregressive. So you generate one token at a time, and you keep appending the output of the model to the input again, and you repeat the process all over again until you are happy with it. The output of a model is not a token. It's not the next token. The output of the model is the probability distribution of the model vocabulary. So it gives you all the possibilities that could be the next token, and then you can do different things with it. You can just pick the most likely token, you can sample, you can do all sorts of things. So out of this block, I want you to look into this tiny thing at the bottom, which is the positional encoding. When you send text to the model, it knows not only the content of the text, the words, but also the relative position among the words. And it is very important to encode the position. You know that the same word in different places of a sentence can mean completely different things, so you need to know about the position. A problem with that is that as you train your model, you train with a specific context length, so you train it with a specific length of sequences, and you can't go beyond that. So for two reasons. Some positional embeddings, you cannot technically go beyond the range because they are trained. Other positional embeddings, they are more flexible, but the model was not trained with large sequences, so it will fail. So it is a very difficult problem to solve, or it was a very difficult problem to solve. There is a very popular attention block. You can think about attention as you, human, do attention. I'm looking at you and I can pay attention to all of you at once. I'm focusing on different places of the audience at different times. Attention works kind of the same way. As you feed text to the model, it will pay attention to different parts of the input. With a small distinction, the model has several heads. You can think of it as the model being several humans, and they can pay attention to different things because they are different humans, and their collective knowledge is aggregated. This block is often the bottleneck in these transformer models. Then the block in blue, which is the feed-forward block, is what made deep learning really popular. So it is a model, this is a block that exists in most deep learning models. And all you need to know about the blue block and the orange block, about the feed-forward network and the attention block, is that their compute scales very quickly with size. So you cannot simply increase their size. It does not scale linearly. It scales faster than linearly, so things explode really, really fast. Okay, so let's talk about quantization. What is quantization? The act of making a model smaller. The models are represented by a bunch of weights, which are numbers, usually represented in 32 bits, but we have realized that we can scale them to different combinations of range and precision to 16 bits and get the same performance while doing, well, not the same performance, but almost the same performance while doing training and inference. With training, you cannot go lower than 16 bits, or it is extremely hard to go lower than 16 bits because training is super sensitive to numerical precision. But with inference, we can go down to 3 bits. So instead of having 32, we can store weights, we can do compute with 3 bits. That makes the model much smaller, that reduces your hardware requirements and makes things much better. There are 2 types of quantization that you should know about. One is the dynamic quantization. It's a type of quantization that you can apply to existing models. You just load the model, apply these algorithms, and it works. It reduces the memory you need to run the model. The folks that developed this method realized that these models have some internal outlier values, and if you keep these internal outlier values in the original 16 or 32-bit precision, while scaling down the non-outlier values to lower bit precisions, you can have roughly the same model quality. Long story short, you get a minimal quality loss, and you get up to 4 times memory saving. This means you can use smaller GPUs, and therefore save a lot of money when running these models. It can also be used with fine-tuning, but I'll talk about that later. There is the static quantization, which is similar in concept with dynamic quantization, with the difference that you need a quantization step before you run the model. So you have your pre-trained model, you do some computations to quantize your model to a lower precision, and then you have a quantized model. It is a much smaller model that you can use to do inference. This strategy has the advantage of also saving the compute you need. You are not just saving memory, you are also reducing the computational requirements when running this type of quantization. But it cannot be used with fine-tuning. So it is not always the best decision to use this. Second group of things I want to talk about, optimization. So before we talk about optimization, we need to understand, like, how can we optimize the models? What's wrong with the models? Why can't the model go faster? To talk about it, I want to show this image, which is a popular concept in computer science, which is the roofline model. The roofline model tells us that all algorithms have one of 2 bottlenecks. They are either bottlenecked by the I/O of the program. The program needs, I don't know, to talk with your keyboard. It needs to talk to your screen. It needs to read from memory. This is I/O. Alternatively, a program can be bottlenecked by the sheer computational power of your computer. Like, your computer cannot do math faster. So each program has one type of bottleneck or the other. And text generation is here. So text generation, the bottleneck to generate text is I/O. Why? Every time you generate text, it generates one token at a time, and for each token that is generated, you have to move the very big model all the way from the memory in the GPU to the compute cores of the GPU. And this round trip is expensive. Because you have so many round trips to make, because you need to do it once per token, the bottleneck of generating text is I/O. And to understand what can we do about it, we also need to understand what is a GPU or how GPUs work. GPUs, as all hardware devices, they have a certain memory hierarchy. You have very large memories that are slow, and you have very small memories that are fast. So usually you have the main memory of your computer, which is also known as the CPU RAM, which is very large but very slow to talk to your GPU cores. Then you have your GPU main memory, which is a little bit faster, communicating with the GPU cores, but it's smaller. And then you have the GPU cache, the orange part of the triangle in this image, which is very small but extremely fast. So if you can rearrange the computations such that your numbers do not leave the GPU cache, you can achieve a big speed up. And that's what the flash attention technique does. So flash attention is a technique created by some folks in academia, where they realize that if they take the original attention implementation and they change the order of operations, the result is exactly the same, but they have to move the model fewer times, or they have to move data fewer times between the main memory and the main GPU memory and the GPU cache. And by doing so, you get a little bit farther away from the I/O bottleneck, and you move closer to the compute bottleneck, which is where you want to be. You always want to be close to the compute bottleneck when possible. With this technique, you get exactly the same model quality. You don't need to do anything to your model. You just change your code to apply this technique, and that's it. You can use it out of the box. It uses less GPU memory bandwidth, which means that your model will be faster. And because it stores fewer intermediary operations, it also requires less memory. So you have a double win. You make your model faster and requires less memory. So win-win. This image is too small for you to look at, and I don't want to go deep, but the folks that created this technique, the technique that they developed is the purple column, and you can see that is higher and higher is better in this image. So it was a very big performance jump when this technique came out. Now, let's go back to the original image. I told you that the model weights have to go all the way from the GPU memory to the GPU cores once per token. That was a complete lie. It used to be true, but now there are ways to work around it. How can we work around it? So you have to understand a certain concept, which is large language models are much faster to confirm that a certain sequence is a sequence that they would generate than to generate the exact same sequence. I'm going to repeat. Large language models are much faster verifying a certain sequence than to generate that exact same sequence. Why does this happen? When you are generating a certain sequence, you need to generate one token at a time. You need to move the model weights once per token from the GPU memory to the compute cores. And when you are verifying a sequence, you can verify you can do the compute with all sequences at once. So you only need to move the GPU from the the model from the GPU memory to the compute cores once for the entire process. So you move away from the I/O bottleneck all the way to the compute bottleneck, which is where you want to be, and therefore it's much faster. So if we can create some strategy to generate candidate hypotheses and ask the big language model to confirm the hypothesis, we are achieving a speed up. And that's what speculative decoding and n-gram speculation do. So speculative decoding can be imagined in the diagram roughly like this. You have your large language model at the bottom, but you have a tiny assistant model at the top. And this tiny assistant model will generate a continuation. It will generate several tokens for a certain input sequence. And now what you do, you just ask the large language model, hey, is this candidate sequence good enough? Do you agree with it? And that's what speculative decoding is. It's the big model will generate a continuation, and it will tell you, okay, I agree with these tokens, that token is bad, let's ignore it. But by doing this, instead of generating one token at a time, or instead of using the large language model to get one token at a time, you can use a large language model to get a group of tokens at a time. But there is a problem. You need a smaller model, and the smaller model is not free to use. You don't always have a smaller model to use. That's why we also have n-gram speculation. N-gram speculation was a very clever technique where instead of asking an assistant model for candidates, you just go into the text that you gave to the model and see if there is a similar or as an exact text as you are generating at the model, and grab the continuation and ask the model, okay, do you want to continue this certain input the same way as you did before or not? So by using these speculation techniques, you can achieve up to 3 times speedup with minor difference. With speculative decoding, you need an additional model. With n-gram speculation, you don't need anything at all. You can use it on any model that you have at the moment. Speculative decoding is good for open-ended text generation, so to generate text to answer to very weird questions, where n-gram speculation is a little bit better when there is repetition, expected repetition in the output. So if you want to generate code, if you want to do summarization, where there is some expectation that the input will also be part of the output. Now, let's talk about architecture. We are halfway through the recent advances, don't worry. So, how can we train our model on super large sequences when most of the data that exists online are small sequences? There are way more Reddit comments than full textbooks. So how can we train models to be good with very large sequences? It's impossible to train a model to be good at something for which there is no data. So what can we do? Remember this very complex diagram. Ignore all of it except that orange yellowish piece, which is the positional embeddings. So models that are the state of the art use a type of positional embeddings, which is called rotary position embeddings, or ROPE for short. It is not a trained position embeddings. It's just a constant that you give to the model, and the model uses that constant to then learn the subsequent part of the output. And you can imagine it as a bunch of vectors rotating. For the mathematical folks in the audience, it is very closely related to the Fourier transform. So some folks on Reddit found out that, hey, if it's a bunch of rotating vectors, let's make them rotate faster and see if we can do something with it. And it turns out that if you make those rotating vectors rotate faster, your model becomes instantaneously better at larger sequences. So it's kind of like the model was trained into a certain sequence, and you are stretching the range for which the model was trained. Of course, the resulting output is not as good as if you have the data and train your model from scratch, yada yada, but it's free. So you can just stretch the context length with which your model was trained, and you can do even more elaborate schemes, as in you train your model with short sequences for which you have a lot of data. You stretch the position embeddings, and then you fine-tune with the large sequences. And doing this, you can massively increase the quality of your model with large sequences. That's why nowadays you can see models that have context lengths up to 1 million tokens, where 2 years ago the maximum was 2,000 tokens. From 2,000 to 1 million, that's a very big jump. Now, another thing that we have seen in the first slides is that increasing the model capacity is very important, because we need our model to know more and more and more to become better. But how can we do it without like exploding the computational requirements? The way that scientists found to do it last year was through a technique called mixture of experts. If you are following news in the large language models field, you'll probably seen this expression. And long story short, instead of having single large blocks, you divide your blocks into many tiny bits, and you train them all at once. But when you are doing inference, you select a small portion of them. So you are now doing sparse computation. And that makes the whole process much cheaper to run at inference time. And the scientists found out that it's also faster to train. So it's a relatively big win. You still need a lot of GPUs to run these models, but these models are much faster to run, much faster to train. So it's a way forward. Like all the recent advances in the last 2-3 months came from this, or the most significant advances came from this technique. Finally, training. So you probably saw that there was a very big performance jump with ChatGPT when it came out. So GPT-3 had pretty much exhausted all data that was available. So how did they go from GPT-3 to ChatGPT? Like, what was the magic behind it? Like, were all like this in November 2022. So it turns out that there is a technique whose name is too long to fit on this slide. It's called reinforcement learning from human feedback. And long story short, you can collect feedback from humans. You see those, when you use ChatGPT, you have thumbs up, thumbs down. You are actually giving data to train the model, because the model will use that data to learn what humans like and what humans dislike. If you look at the capacity of model to complete text, which is the original task for which these large models are trained to. They are trained to complete text. The model doesn't become much better, but the model becomes much better at doing what we humans like, and at the end of the day, that's what we care about. So these models learn what humans like and dislike, and therefore we are optimizing the model for our preferences. It can grab existing pre-trained models, but the pipeline is a bit more complex. So usually we were stopping here, or even here if you had a lot of money. This is all the data that you have about text. It's the whole internet. Then you could select some high quality data to fine tune your model on, and you get like a decent model. But this decent model, GPT-3, was not good enough. So the way to go forward was to collect simple thumbs up and thumbs down, and you could massively increase the quality of the models. Now, training is a lot of fun, but is extremely expensive. To give you a ballpark, you need 9 times more memory if you are doing trained, or usually you need 9 times more memory if you are training a model compared to just using the model. So if your model fits roughly, barely fits on a GPU, now suddenly you need 9 or more GPUs just to train your model on something. And that's really, really expensive, because the costs of having more and more GPUs, they don't scale linearly. You have to put all the interconnect between GPUs and all that. So it's expensive. So what can we, GPU poor folks, can do about it? We can use a technique developed recently called low rank adaptation. So the folks realized that using a model, so having pre-trained weights, is relatively cheap to use. It usually requires 2 bits per model weight to run a model, but it requires 18 bits to train a model. So they realized, okay, what if we keep the pre-trained model frozen, and instead of modifying this pre-trained model, we just add a bunch of weights, and we train those weights. So instead of requiring 18 bits per weight here, now you only need 2 bits per weight here, and you leave that 18 bits per weight on that very small portion. So you essentially append new weights to the model, and you train those new weights. By doing that, you drastically reduce the training requirements. You can now use small GPUs to train large language models. And you can even use it with quantization, remember from what I talked before. And when you use it together with quantization, you are able to do things like training 65 billion parameter models, so really, really large models, on a single GPU. And that's extremely powerful. If you have a company that wants to use large language model on a niche problem, you can easily fine-tune existing models to that niche problem of yours. You don't need a whole server to do it. You can now do it with a consumer GPU. And that's it. To end this talk, I want to talk about trends. This is futurology, and as with all futurology, I'll probably be wrong, but these are the things that I see moving on forward and grabbing some attention. So the first trend I want to talk about is agents. So at the moment, if you ask a large language model, how many people live in the capitals of Switzerland and France combined, your model will probably give you a terrible answer, because there are many steps you need to figure out the answer to this question. You need to know what are the capitals of Switzerland and France. You need to know how many people live in Bern and Paris. You need to be able to sum. Mathematical operations are extremely difficult for these large language models. So what can we do? You can leverage external pieces of software, usually called tools, to enhance the performance of your model. Your model will act as an orchestrator, and it will request the use of certain tools as needed. So in this question, the model will probably go to the internet to first search what is the capital of Switzerland and France, then goes again to the internet to know how many people are there in Bern and Paris, and then use a second tool, a calculator, to add the population in these two cities. And by doing this, it is very difficult to do in practice because you need to train your model to use these tools, and it is very difficult to do so. But when you are able to do it successfully, the model gets a much higher quality on these type of factual tasks. A second trend I want to talk about is multimodality. So I've talked mostly about a model that takes text as input and gets text as output. But what if we do this? What if we have all types of data going into a model, and the model is able to return, which is a very abstract concept, but what if the model is able to return all these types of data? We now increase the amount of data that we have to train our model. Instead of being limited to all the text that exists on the internet, you can now grab video and ask the model to predict what is the audio corresponding to a certain video. You can take text and ask it what is the audio that it corresponds to a certain piece of text. And this can be as if you have a description of a beautiful mountain with trees and birds, it can predict the sound. But if you have text as humans speaking to each other, the model can predict speech. So there are many, many tasks that you can do when your model becomes multimodal, which means that there is much more data to train your model. And in theory, the model should be able to share some internal representations among these modalities. To give you an example, a recent model called Fuyu, their creators realized that, okay, it's hard to make a model understand simultaneously image and text, but what if I convert the image to a text lookalike? What if I try to convert an image into tokens, this abstract thing? So their creators realized that they can slice the image and add a special layer that converts image into some form of embedding, some form of tokens. And then you have a simple text model, and the model digests images as if it was text. And by doing so, you can do a little bit more complex visual tasks. If you just ask a random model, what was the fair amount of paid vacation days in the United Kingdom? The model will be like, I don't know, it will give you a random number. But if you feed him an image containing the answer to that question, and the model can digest the image, then it's a trivial answer for the model. It can just go look in the image. And that's it. I hope you have enjoyed this talk, and I'm open to questions.
Thank you for your keynote. Questions, okay.
I hope this was not too technical. I tried to make it as non-technical as possible.
Hello? Yes, okay. I didn't think it was technical. I thought it was a great presentation. My question was on the multimodality that you are now presenting at the end. You presented that way in which we could transform images into a kind of text to be able to have a model that can interpret images and text. But if we wanted to have a model who could interpret, let's say, a major diversity of inputs, such as audio, and to better mimic what a human can do, will this be a viable way to do it, or will we need another way?
So I think there are better ways to do it, but there is a reason why we are using this strategy. It's because we have really powerful language models, and when you have a really good hammer, everything is a nail. Mm-hmm. So you just transform what you have into tokens, and you already have a powerful model. You just need to train that a little bit that adapts images to text, and then you can use your pre-trained models.
But do you think that in the next years we will have to find another ways, or will this hammer always be useful?
It's a very difficult question, but if I had to put my money on it, I would assume that yes, we would use this strategy.
Okay, thank you.
Hi, João. Thank you for the presentation. I also had a question about one of the future trends you were predicting, about the model being able to call all kinds of internet services, say APIs, any external component. My question is, why do you think it's not that easy, at least right now, to do so? I mean, like, just to call an external API, what are the hardships, maybe the things that we are not seeing here that make it so difficult?
So there was a paper by the Meta team last year where they were probably this was probably the paper that brought this topic into more common discussion. And to train a model to use external tools, they had to create a synthetic data set where the tool was used to solve a problem. So it's all about data. To know which tool to use, the model has to be trained to use that tool. And you don't have text online saying, hey, I'm using a calculator to derive this value. You just have people doing math. So it's extremely difficult to craft data sets in which the tool is used so that you can train the model to use the same tool. That is the biggest limitation.
I've actually also seen a paper from some folks from Berkeley. What they did, they used it on VQA, so visual question answering. And what they did, they used LLMs to actually generate the code that would call the APIs to answer the questions in the first place. But the catch here is that they had to take some few shots, human annotated prompts, so that there was actually human effort. It was not automated.
Yes,
so the guy
correct.
had to, yeah.
So that is the workaround. When you don't have data to train your model, you can try a few shots. So you can give a few examples, and these models are really good at taking few examples and doing something meaningful with them. So that's an alternative.
Thank you very much.
But still, you need to craft the data for the few shot prompt.
You still need humans for that.
Yeah, exactly.
Yeah.
Yes.
Thanks.
Next question.
Thank you. I have a question that is, nowadays with more text being generated by AI, more text will appear in websites and everything. So how will, given that AIs will likely get data from websites, how will that affect the developments and the training?
So there are two group of people there are two answers to your question. There are two group of people. I'll try to give you my unbiased answer, and then I'll give you my biased answer. So the unbiased answer is that you can consider that you will be plateauing the quality of data that exists online because everything will be regurgitated from ChatGPT and other similar models. So that is the upper bound of the quality for the bulk of the text data. There is another group of people that believe that models, as you have these thumbs up, thumbs down, you can train separate models to work as evaluators, so to predict whether it is high quality or low quality data. And there are a few papers where they just take data, they train a model, then they train an evaluator, and then they use the original data with the evaluator model to give it thumbs up or thumbs down, and then repeat the process with the filtered data, and then do it again. And what they realize is that the quality of the resulting model goes up. So there is a chance that models can become their own evaluators, and then they gradually improve without any human intervention. I am a believer that this cycle is possible. So if I had to put my money on it, I would think that is not a problem. Like generating a lot of text is not a problem for the quality of our data sets.
Thank you.
Hello, my question is a bit more on your work and not exactly the talk.
Mhm.
What was the process to entering and working on Hugging Face?
That is a good question. It was a spontaneous application. I happened to be lucky to have exposure to the sort of technologies that they were needing at the moment, and that was it. There was no secret. I would say that if I had to give you like a secret sauce, is do what you like, because you are always motivated to do what you like, and therefore you learn faster, and therefore you can get into better positions.
Thank you.
Any more questions? Okay, guys. João will be in the showcase area after, so you can ask him more questions, and that's it. So now we can sort the winner for this session. I just have a note: the Echo Pop cannot be shipped to Portugal, so we will instead give you an Amazon card, so you can buy whatever you want Just not an echo pop because it just not arrived here. And the winner is laptop. Nice. Okay, so outside we can give you the card. And next we'll have a keynote from Nemanja. He's from Google DeepMind, so come by in 10, 15 minutes. And a round of applause for João again.